Yes, that means it's going. Okay, thank you for coming this evening to the 8th Annual Computer Science Club Meetup thing. Not annual, but whatever, it sounds fun. I'm Colin Shaw. Thank you to Rev Unit, Mike Caldino, for sponsoring the food, the location, the flooding. Sorry, just kind of acting silly here. So in the last two times ago, we used OCaml to build a multiple layer perceptron sort of situation for training neural nets. And a couple things about that, we discovered that it really had a very nice feel to it with the syntax and the abstractions, but the performance was not really spectacular. So in the last episode, we looked at why the performance of a functional language for things like evaluating and training neural nets, which are basically matrix arithmetic, don't perform quite as well as some imperative languages. And we made comparisons between using OCaml and some of its abstractions and C, and then benchmarked it against some old Fortran code. So this meetup is sort of a two very different part thing. The first part is continuing this performance analysis sort of trend with looking more at the CPU and how we can eke out performance for anything, but mainly problems that are sequential access patterns like matrix vector multiplication. And then in the second section, looking at one question that I've had, which is, how long does it take me, how many iterations does it take me to train a given neural network to a reasonable tolerance? Because if I have a certain problem, how do I know if I have fast enough hardware? How do I know if I can do it in a reasonable amount of time? So we'll look at that, and then look at reducing a feature space for a smaller neural network. So the reasons we might be interested in some of these issues are just knowing if we can solve a problem in a certain amount of time, and things having to do with cost. Like if I can assign some sort of cost, either a monetary cost for purchasing a fancier computer, or there's some other kind of metric that I'm using, like I want to be able to do something in low power, I want some sort of knowledge of what problem I can solve with that. So where we're starting on the computer stuff is we're going to look at cache. We're going to look at the processor and caching and pipelines and compiler settings and that sort of stuff. So in a processor, there's the core, which generally is comprised of the ALU, the floating point unit, the memory decoding, the TLB, pipelining sort of stuff, and a bunch of registers. And these days you probably have, well, there's a variety of different types of register, but for any particular type of task in the ALU or FPU, you probably have between 8 and 16 registers on most modern processors. So when we're talking about cache, I'm lumping registers in this spectrum as this kind of closest to the core, fastest memory, where you can stick something possible, all the way through main memory, which is the slowest and largest. So sort of the baseline, sort of for thinking about the timings on this, I'm going to use a 4 gigahertz processor, which has a 1 cycle access time for a register. So your access time for a register would be about 1/4 of a nanosecond. The L1 cache is usually separated into an instruction and data cache, but this isn't true for all processors. Processors implement these things however they want to, and processor designers have different choices based on what market they're wanting to put it into, what technology they can fabricate, what cost they want to introduce the product at, and so forth. But a good desktop would have a separate instruction and data L1 cache. They're implemented per core, fabricated on a processor die. Back in the day, up until about the 386, you didn't really even have cache because there wasn't much point. CPUs were slow, memory was relatively fast comparatively, so you didn't even really see that. After the 386, you started seeing off-processor cache. Today, this is unheard of, really. Even your phone has pretty substantial cache on core. But usually L1 cache is anything up to about 64K, and it would usually have an access time of about 1 nanosecond. So it's slower than the registers, but it's pretty good. L2 cache, which kind of in the hierarchy of cache, the further out it's getting, the further from the core it is, the more space you have for implementing it, so you can have a larger cache, but the access time becomes worse. L2 cache pretty often is a blend of instruction and data cache, so you're not having a separate instruction and data cache. On higher end processors, it's fabricated per core. On lower end, it's usually split between the cores. It's on the die, and it's usually about 256K to single digit megabyte with about a 5 nanosecond access time. So already by the time you get to L2, you're 20 times slower than register access. L3 is blended between instruction and data. It's generally shared between cores. On any decent processor, it's implemented on the processor die, although there's a lot of processors which would turf that off as a side thing. Usually it's single digit megabytes to tens of megabytes. So like for example, like I have an i5 4th generation at home and it has 6 megs of L3 cache. Let's say a high-end Xeon might have 64 megs of L3 cache. Generally a power of 2 until about the 3rd generation Intel processors where they started doing like the 6 meg of cache thing. L3 cache tends to be maybe about 30 nanosecond access time, so over 100 times slower than register access. There's this idea of L4 cache, which isn't really in the same vein. Back in the day when GPUs started being pretty powerful for 3D rendering, what happened was you have an arrangement between a processor manufacturer and a GPU manufacturer where you'd have an allocated bit of memory that was shared between the two. So you could load textures and so forth to it, and then the GPU could do its thing. And so you had a memory mapped location that was shared between both of them. L4 cache is in that same vein. What they do is they have a very wide bus for this L4 cache, so it's not really main memory, it's its own separate thing. But it's that same design idea of having it shared mapping between processor and GPU. And the focus isn't really the access time, it's the bandwidth. So they make as wide of a memory bus as they possibly can get away with. And then they claim it's a very exciting new feature that's never been heard before in the history of the world, even though in the 90s you'd have the same thing going on, you just wouldn't call it L4 cache. Then you have main memory, which is of course a blend of instructions and data, shared between everything on the motherboard. It's clearly not on processor because you get dim memory to put in your box. And for a workstation, like a typical workstation, you might be able to have up to 32 gigs on it. But what's really fun is looking at some of the specs on some of the high-end processors. Those high-end current Xeons, you can have 16 CPUs on a motherboard and address 3 terabytes. So it really depends on how, like, which processor you buy and how many pins they bring out for addressing memory. Main memory typically on a workstation would have about 100 nanosecond access time, and if you're something sort of typical, sort of entry-level RAM like PC 1333, you have about a 10 gigabyte a second bandwidth with it. So that's really pretty good, but it's still worth noting that that memory access is 400 times slower than a register, and 10 gigabyte a second is really pretty good, but it's nowhere near what you get like with the L1 cache. Just to put some of those figures in perspective, a solid state drive has an access time of between about 10,000 and 100,000 nanoseconds, and sustained throughput of about 500 megabytes a second. So it's access time wise 100 to 1,000 times slower and a 20th of bandwidth. And a rotational hard drive has an access time of about 5 million nanoseconds and about a 200 meg sustained throughput. So whenever you're thinking about a problem, like I really want to solve this numerically intense problem quickly, you don't want it to be running on anything other than memory because it's pitifully slow compared to memory. So we talk about cache. How does the cache work? Caches are broken into a cache line. When you load a value, you think you're loading a character or an integer or whatever, but you're actually loading a whole cache line. And the size of a cache line varies considerably between processors, but typically is between about 16 and 128 bytes. So on a, say, an i5 or i7, you're loading 64 bytes at a time. You think you're getting just the one character, but you're getting, it's adjoining 63 characters. On smaller processors like the ARM processors, they usually have the smaller cache line size, like 16 byte. Caches, the way cache works is actually all of the three things that I'm going to mention are basically the same thing. It's just different regimes of doing it. So basically they're all variations on associativity for the cache. So there's three generally spoken of types of cache. You can have a direct mapped cache, where if you have cache then you've got main memory, then whenever you select, you're wanting to look something up from main memory, it's not in the cache. It realizes this and it fetches memory to that cache. Well, the mapping is just sort of direct. There's this, say, 16K of cache, and it maps to one and only one point in memory for that 16K. So, for example, if you were doing a sequential problem, this works okay. But if you were doing something like adding two large arrays together element-wise, where they're much larger than the size of that cache, when you load the first one, it's in cache. You load the second one, sorry, it's not in the 16K. You're going to invalidate the cache and have to reload it. So the complete other end of the spectrum is having a fully associative cache, where every byte in the cache can be mapped to anywhere in main memory. So you don't have any of this cache thrashing problem, but it's very expensive, complicated, and slow to implement fully associative cache on a processor, especially if the cache is large. So the compromise that's generally reached is to have n-way associative cache, which is like breaking your direct map cache up into n smaller chunks. And how this is good for your problem is, since you have, say maybe n is 8, if you have n being 8, and you have two things where you're taking two lists, two arrays, and element-wise adding them, the first hit comes from the first section of that cache. The next one will map out of the next section of the cache. If there were more, they'd map out of the subsequent ones until you have at least 8 things, and then it would have to recirculate the cache, invalidate something, and refresh it. So it can be shown, of course, that fully associative cache is the best, but somewhere between about 4 and 8-way associative solves most problems pretty well. Typically, in real life, you see associativity between 2 and 16. And one thing that I think is pretty interesting is a lot of the market segmentation between AMD and Intel has a lot to do with the cache, both the size and the associativity. Intel tends to have 8-way cache for L1 and L2, and then higher, like 12 or 16-way cache for the L3. And AMD tends to target a different market that's not numerically intensive applications, and they have a simpler L1 cache that's only 2-way associative. So what their focus is they're not really interested in developing something as complicated for the L1 cache, but they tend to have a higher associativity, like 16-way associative cache for L3.
So what kind of customers then is AMD targeting with those types of processors?
They tend to target a person more in the server market, where the way that they would anticipate you using their processor is maybe you loaded an image from disk, or it was cached somewhere or something like that, and you'd have a fairly large L3 cache that would have the ability to fetch and keep in cache something like an image or a page. Whereas the Intel idea is more of you're wanting to do, well, I mean, they support that because they have fairly high associativity, but they also have high associativity on the lower level caches. So they have better performance generally for numeric applications. There's also a doohickey called the translation look-aside buffer, which is somewhat like a cache, but not really a cache. Whenever you're referencing memory, memory comes in different flavors having to do with the paging and how it gets indexed. And if you're having to do a calculation to determine where in memory, how you're addressing memory to fetch it, every time you're trying to fetch something from memory, it takes a while. So the TLB is just a dictionary sort of hash, or cache, if you will, for those lookups. So it's not really cache, but it's a cache that helps with memory lookups for physical memory. One thing else we're thinking of is processor pipelining, and we're not going to go into it particularly in detail because it's something the processor really does for you for the most part. You can give some hints, mostly having to do with the way you present it with data and instructions. But in a processor, you're going to have to load an instruction from memory. The instruction might refer to some data that's loaded from memory or in a register or something. It'll execute something, I mean the actual operation you're wanting to do, adding or subtracting or whatever, and then it'll have to write a result somewhere. And that result could be memory or register or whatever it happens to be. So one way of thinking about the pipelining, I think it's kind of fun, is thinking about the grocery store and the checkout lines. So if you only have one pipeline, that sort of is not how you want the grocery store experience to work. You'd like the grocery store experience to be something where there's somebody with a big basket and you've got the little speedy checkout basket. It would be nice if there was a open pipeline or queue where you could actually get through in a more timely fashion. So that's basically the metaphor for how the processor does some of its pipelining, except how the queuing happens and the strategy for the queuing is substantially more complicated than the decision you make at the grocery store. But it's still somewhat the same. The processor will know whenever it loads an instruction that this is something that would take a fairly long time. So it would know for subsequent instructions that are smaller that this is not the queue and the pipeline to get into. So generally a processor has one unit that's for relatively heavy instructions and then several other pipeline units that are for lighter weight instructions. And that way it can dispatch a heavyweight instruction into a pipeline that will execute slowly and then accommodate these others. Yes?
I just got my head in an infinite loop.
Yeah.
So what does the analysis before, like what figures out which pipeline it's going to go to?
A lot of logic that's in the pipelining mechanism. It will.
So the pipelining mechanism is not the processor. That's or a part of the process. Whatever.
Part of the processor.
Okay.
It's not where the actual like operation for addition occurs.
It's just analyzing the instruction that's coming in, determining what it thinks it needs, and then dispatching it. The processor still does it. Okay.
And it's a little bit like if you, oh gosh, I can't believe I'm going to say this. If you remember from Price is Right, it's a little bit like Plinko.
I remember.
Because
What now?
where you put the disc on, over the nails and it kind of bounces down and you win a prize. It's a little bit like that. It's not something where the processor is just sort of all of a sudden making this determination. On a modern Intel processor anyway, the pipeline is between about 12 and 24 steps. So whatever is actually executing doing an addition, there are things that are in the pipeline 24 instructions prior to it that are being considered as to how they should be executed. And it'll take into account things like, is this going to have the same cache line hit as this other one? Maybe I can shuffle these guys around and have a lot better performance. Is it a big instruction? How am I going to dispatch it to whatever size register it's asking for? And generally, if there's some need for waiting, it'll put a no instruction in there that does nothing just on its own. So you don't have to code these up, but if there's 5 cycles in a pipeline that need to be held not doing anything, the processor will just fill it up with no op instructions.
Is that the same thing as branch prediction?
It does do branch prediction.
Oh yeah.
So there's a lot that the pipelining will do. It'll do preliminary evaluation, like you said, on branch prediction, so you can see it will kind of have a best guess on how the code flow will go and what would need to be loaded next. So that's really where a lot of focus on the processor engineering is anymore. And it's amazing to me, between seemingly very similar generations of processor, how vastly different they are on how the pipelining works. You can have two like temporally adjacent processors that come out to have completely different pipelining, and one will have better performance for some things and one will have potentially better performance for other things. Also somewhat related to this are the vectorized instructions, at least for the floating point unit, which are relevant to us since we're interested in math stuff, or at least for this presentation. So probably in the 90s-ish, MMX instructions came out. And then we also now have SSE and AVX instructions. And the idea with these are, what if I have a floating point unit that can compute double precision floats, but I'm dealing with all of these single precision floating points? How come I can't just make a new instruction where I'm packing two singles into a double, and I can switch between either using it as a double or two singles? That way I can get twice as much stuff done, and I'm using a smaller type, so I have better utilization of my memory bandwidth. So that's the entire point of those instructions. And generally, they're compiler flags they have to specifically turn on to use them, but they make an enormous difference. So what environment makes our numeric code fastest? And what kind of decisions can we make about purchasing hardware? We need fast memory. It's probably one of the most important things of the whole deal, especially for if you're investing in a relatively powerful computer to begin with, because and if you're doing large problems. If you're doing very small problems, it's not really the dominating factor, but for a big problem, like if you were multiplying a 10,000 by 10,000 matrix by a vector or something, it would be a dominating issue. You want sequential accesses since you want to get good cache line performance, and you want to basically buy the fastest memory you can possibly afford if you're doing big problems. As far as like register and caching and so forth, you don't have as much control as you do buying memory, but if you had the decision between processors where one had more and one had less registers, with more registers you have more of an opportunity for fast storage of loop counters and intermediate values and so forth, and you probably want to buy a processor that has the biggest cache that you can afford and the highest associativity. And so that can be a pretty wide range, because something that's like a perfectly adequate i5 may have an MSRP of $200, but then these high-end Xeons, they're just crazy. The one that will address 3 terabytes is like $7,000 for the processor. So you've got to kind of justify the amount of cache too, but on the whole, the more cache, the better. And a fast processor. One thing to kind of look at is the relative speed of memory and processor, because I've done, like, we'll see there's some kind of speed comparisons with Raspberry Pi versus an i5, and Raspberry Pi has relatively fast main memory and consequently relatively slow compared to memory processor, and has a whole different dynamic on how it executes numeric code. But generally, as with all of these, you should probably buy the fastest processor you can afford. And then you should have intelligent choice on what types for the numeric types. So traditionally, you've got single precision 32-bit and double precision 64-bit. And you have more exotic types for people who want more precision, the long doubles and so forth. But anymore, these half precision 16-bit floating point numbers, which started really with the GPU crowd. One thing to think about with these is they're not always the right solution. Most processors other than GPUs, 16-bit floats are a storage format, not a computational format. So like on an i5 or i7, you might store things as a 16-bit float, but it has to be promoted to 32-bit float, then computed, then converted back. And that has a cost associated with it. So what's kind of funny about 16-bit floats, because they're kind of hyped up, it seems a lot at the moment, is if you have a small problem that's smaller than the L1 cache, it actually performs about half as fast using 16-bit floats as single precision because of the conversion cost. But if you have a very large problem, it'll compute faster. But of course, you've got to be sure that your problem works well with the lower precision. So most processors have those anymore. Intel has them, ARM has them, GPUs have them, but they might not always be the right choice. Another thing that's very important is, say you're doing matrix multiplication, is how you organize the matrix and how you step through it to do the arithmetic. So if you had a matrix and it has a row vector and you're multiplying it by a vector, some column vector, basically dot producting these, then there's two ways you could have organized this matrix. On the one hand, you're stepping sequentially through that vector, and you're getting excellent access patterns. The first time you read something, one of the numbers, you're getting the number, but you prefetch the entire cache line. So the next one, you're getting L1 hit, L1 hit, L1 hit. On the other hand, if you organized it the other way, you'd be skipping the size of the matrix row every time. So you'd be fetching from main memory, fetching from main memory, fetching from main memory. That's tough to say fast. And you have substantially worse performance. So paying attention to if your design is column major or row major is very important. Beyond that, you just need to be aware of the support for vectorized functions. Make sure your compiler will participate in inlining functions whenever it compiles them, because there's no good reason you have a simple numeric function that you're computing, but you have a function call to get it done. What kind of type support? Like, for example, if you were interested in doing 16-bit floating point, the Intel compiler is the only one for Intel that even supports it at the moment. So you have to make decisions based on the tools too. Now there's this opportunity to look at code that's basically for looking at performance of cache and pipelining. And I'm not really convinced it does anyone any good to look at the code. So I'll just talk about it, and then we'll look at the results from it here in a little bit. So there was one program that was put together for looking at a cache line. And so what it does is it does an increment operation on a floating point, and it does it first, like it's all in single precision. So at first you take every next single precision sort of in order, and then you start skipping every other one, then every fourth, then every eighth, and you see how long it takes, and I'm returning it like in megaflops for its speed. And so at some point or other, when you get to skipping more than the size of the cache line, the successive computations you're doing are not coming out of the L1 cache because it was bigger than that cache line. So you can see the performance sort of start and drop down after you get past the size of the cache line. The next program looks at the cache speed for all of the LX caches. So it just does a sequential collection of adding floating point numbers. And so at first it does, in this case, 256, just a little chunk of 256 floats. Then it'll do a pass with 512, then 1024, and then all the way up to bigger than L3. So it starts smaller than L1, ends bigger than L3. And then you can see the speed, you're getting L1 kind of hits, and then you're getting L2 hits, and then you're getting L3 hits, and then it just goes downhill when you are actually doing problems that are bigger than the L3 cache. It's really kind of amazing how much of a difference it really has in practice, because you can have like a 20-to-1 performance difference between a small problem that's in L1 cache and something that is larger than the L3 cache. And then there's some pipelining examples where some of them are looking at the difference between if you have one memory element that you're doing, say, 4 additions sequentially to, versus having 4 memory elements that you're doing one operation on, because these will get pipelined different. The processor will say, oh, I see that you're accessing the same memory. Maybe I can help you with that. Versus the other one, it sees that they're different, so it will take a different strategy for doing the computation. On some older processors, if you flip the order of operations, they'll have different pipelining strategies, so they would have different speeds for the results. So there's an example of that. And then one thing that's very important for threaded applications is to look at the cache line hits. If you have, and this, it kind of seems a little counterintuitive that if you had a threaded application, if it was using the same cache line, the performance would be terrible, but it's trying to keep you free of side effects. So if one thread were to access some data, it loaded it into cache, L1 cache, then wrote a value back, and then another thread might be interested in something in the same cache line, that cache line would be invalidated because it knew that the prior thread just wrote to it. So we would consider this to be untrustable memory, and so it would invalidate the cache and read from the main memory again. So if you're doing a threaded sort of situation, a lot of times you just chunk your problem up and you never even have this issue, because it would be, maybe you have some big array that you want to do a computation on, and you just divide it in half and have 2 threads each doing half of it. But it is worth being aware of that if you have 2 threads operating on the same bit of memory, it can perform much worse than if you just had a single thread. So best practices are smallest possible type that meets your program's requirement. The big types for floating point generally were for engineering, like bridge building and so forth, people who wanted a lot of precision. But anymore, we see a lot more problems that don't demand that precision. So the smallest type you can get away with will get better performance out of memory. It'll avail a lot more of the vectorized operations. Tight loops that you've thought of, I mean, you've really reasoned out that this loop is going to perform how you want it to, and it's the simplest, tightest loop possible. Make sure the compiler supports function inlining, and the compiler choice is a pretty important one. Generally, a major manufacturer, like picking on Intel, provides the best compiler, though they like to charge money for it. It'll produce the fastest numeric code. Next up is one of the more generic compilers, GCC or C-line, using optimizations, and then basically any of them not using optimizations. And it's amazing how much having the optimizations make a difference. Last time we looked at some OCaml, but we didn't look at integrating it with C, so we've got an example of doing that. Basically what happens is you compile against the OCaml headers, and it provides some stock functionality for converting OCaml types to C and talking to the garbage collector, both on the coming into the function side and the getting out of it side. So it's really easy to extend OCaml with some kind of wonderful, fast-tuned procedure to run. Ooh, this is fun. This one's all over the place. It seemed like it was going to be like this straightforward thing, but it's just sort of all over the place. Processors and their speeds, and why are they slowing down? It just seemed natural if you're talking about cache and stuff, that what's up with this? And this is probably one of the more interesting things in this presentation. So speed of light, if you're a 1 gigahertz processor, 1 cycle time is a nanosecond, and the speed of light in a vacuum is about a foot for a nanosecond. EM wave in a wire is probably about 8 inches or so. So one thing that sort of limits processor performance is the fact that you're kind of getting close to, like, the distance between the core and like L1 cache is kind of getting close to like where that 4 gigahertz really equates to only a couple inches. I mean, it's not, it's more like maybe a centimeter or something, but it's getting into the ballpark where the actual physical distance makes a difference. And when it comes to things like external memory for main memory, you've got to get the entire memory bus to work in a noisy environment at a reasonable distance. So there's a little bit of a limitation coming on with just distances and speed of light. But with the processes that are made, you have a silicon gate with generally silicon dioxide insulation under it, and then a silicon channel, and the charge on the gate controls the conductivity in the channel. Now we're seeing these structures get smaller and smaller, and as you shrink the structure, the area of the gate shrinks quadratically, and so the thickness shrinks quadratically. And by the time we're where we are now with 22 and 14 nanometer features, the gate thickness is 1 molecule of silicon dioxide thick. So what do? What the processor designers are doing is looking at other materials. So instead of using silicon dioxide, which is cheap, plentiful, and reliable, they're looking at other materials that have different properties, because you can't shave that single molecule in half to make it smaller. So we're actually at about 14 nanometers. You're at about the time where you can't physically shrink the thickness of the insulation on the gate. Also, the RC time constant from the gate with the connection to the previous logic, it's in silicon, which has high resistivity, and is usually a Manhattan distance going, you know, horizontally and then vertically to the gate. So this becomes an issue because you need to reduce this. So in order to be able to effectively move the charge fast enough. So what's being done is looking at using metals instead of semiconductors for that, and using point-to-point. So instead of using cheap silicon, people are now using like point-to-point palladium wire. Well, that's going to make it a lot more expensive to make these processors. And heat generation, the faster you go, the more charge you're moving, the more heat. As you shrink the features and you increase the frequency, the thermal, you know, the heat generation density becomes substantially higher and the temperature gets higher. So what's generally been done to compensate for that is to lower the voltage. But, I mean, it's silicon, it's a semiconductor, so you can't lower it below the band gap. And we're already seeing processors that run it just slightly over the band gap. So what do you do? These guys that make the processors are in a pretty interesting pinch because they're making things where they're at the atomic thickness level and trying to make it smaller. They're at the level where you can't fabricate things very easily. And the other thing that's worth noting, I think, is that 14 nanometers is smaller than the smallest known virus, and it's a 40th of the wavelength of green light. And how they fabricate it, it used to be, you'd like, way back in the day, like original, like the 8008 processor, it was like hand-drawn and basically photocopied smaller and smaller as the lithography out, template, which you would then expose the silicon with. Nowadays, there's nothing that has the kind of high frequency that you need for doing it. So instead of just making a mask to outline the silicon to etch it, for something that has billions of transistors in it, you design a diffraction grating because there's no light source that's quality enough and small enough wavelength to do it other than diffraction. So you can't just draw a square, you draw like a square with a little notch and a little notch so that when it's exposed to extreme ultraviolet, it actually projects into what you want it to be. And the other thing that I think is pretty interesting is there's projections that will see 5 nanometer features by 2020. That's kind of doesn't say much by itself, but the surface roughness of atomic silicon is 1/4 nanometers. So by 2020, you'd have reliable devices that are made that are only 20 times the width of the surface roughness of the material it's on, which is crazy to me. So the challenge in making some of these processors has gotten pretty substantial. And probably in the last 10 years, the speeds haven't increased more than about 1 gigahertz. I mean, nowadays you see commercial processors that are over 4 gigahertz, but they're moving slowly, and they're getting wider with number of cores instead of faster. So
We should increase the speed of light.
that would be a good solution to this problem, and we should make silicon dioxide shrink a lot. But some of the ways to overcome this, there's no long-term solution. I mean, for decades, they've kind of gotten away with, well, we can shrink it, shrink it, shrink it. But at this point, once you shrink it to the point that it's one molecule thick, you can choose other materials, but you can't just keep choosing them. There's only a finite selection of materials that would even work for it. So they're not going, I mean, maybe you get a 2-time performance gain choosing a material that's 10 times more expensive, but where do you go after that? I mean, regardless how you perceive it, there's a kind of limit coming on processors. So I guess after this little next section, we can look at this performance stuff, because it's actually pretty interesting, like how wildly different the performance is using optimizations and not, and having good cache performance and not. But switching gears kind of back to where this all started with this OCaml neural net business, as has been mentioned before, and I have started at this point, I decided I would like to make a little robot that can drive itself. You can train it to drive itself. So I've started working on this project. And one troubling thing is, like, Google did a very nice job with the self-driving car, but they have this presumably astronomical amount of driving data from the street view cars driving around. And I don't have that driving data. And they have more computers, and they have more money, and they have better cameras, and all sorts of things that make you feel foolish starting on doing this project. But how can I do this and not spend forever and not have to have all this data? So the big question is, what size problem can you actually solve in a reasonable amount of time? So I figure I can get 3 frames a second where it's captured, processed, controlling the vehicle and all this sort of stuff. 3 to 4. I mean, you know, you can get 30 off the camera. 3 to 4 in reality doing everything sounds like a good guess. And I don't have a high attention span, so 10 to 15 minutes of training is the max for me. I don't want to go out on the sidewalk driving it around all day. I'll run out of batteries or something. So it's got to do it pretty quick. So if I'm wanting to train a neural net in about 2,500 training iterations, how big can it be? Was a question that I had. So if you consider it's square, it's going to come from video. So I'm going to say the input feature is n by n. So what's n? And it's got one output. It's got the steering, some kind of real valued thing about steering. So what I've learned is, if you consider it a black box, the degrees of freedom are the total number of inputs plus outputs. So it's n squared plus 1. And I've decided that one hidden layer will have n neurons in it, because that matches my perception of how I look at the sidewalk. And I'm looking at it kind of going down the sidewalk, which is kind of the vertical part of the image, and I'm charting out something about the curvature. And then in the second layer, it'll have 2 neurons. And that's because if I'm thinking about making a turn on the road, there's some measure of curvature, some measure of offset from center. Something between these two makes me steer a certain way. So it's nothing other than just sort of a general guess that these might be good starting points, but 2 layers, one with n neurons and one with 2 neurons. Every neuron in any layer is independent of the others, so they multiplicatively add to the degrees of freedom of the whole problem. And because you have the nonlinear activation function, the layers are also decoupled from each other, and the result is this total number of neurons that are hidden multiplies the degrees of freedom by that number. So there's n squared plus 1 degrees of freedom in the problem being solved, multiplied by n plus 2 neurons that are hidden, gives you basically n cubed degrees of freedom for the problem. So what you can say is that n cubed is proportional somehow to the time it takes to do the problem. And reading in the literature, that proportionality tends to be between about 2 and 10, and that depends on the learning rate that you're using and how difficult the problem is to solve. So I don't know how difficult the problem is to solve, and I'm not sure what learning rate I'm choosing, but I could kind of conservatively choose something right in the middle, say 5, maybe solves this problem. So if I do that, then n would be 8, give or take. So if I want to solve a neural network, it's got to be an 8 by 8 input, which is pretty pitiful video, which brings us to the last little topic, which is pre-computation from the video. So I can capture a frame of video, and if I just shrunk it to 8 by 8, I would have no idea what I was looking at, because there would be no resolution. And there would be interesting aliasing artifacts, I'm sure. And I don't think that that's the kind of data that would work too well with it. So what I'm thinking of is you take it, the original frame, and you make it into 8 by 8 boxes of larger numbers of pixels. And you blow the contrast out so it's all black and white, and the sidewalk's white and the grass is black. And if you have a sufficient number of black and white pixels, like maybe between 25 and 75% or something, enough so that you're not dealing with something that's a pebble in the grass, but you have an adequate amount of sidewalk in the grass, then what you could do is, I might draw a little picture. I might not draw a little picture. Anyway, you have black region and white region. You can find the centroid of the black and white, draw a vector between the two, and the perpendicular points along with this edge of the sidewalk. And if you do that, you're turning this problem into something that just has an 8x8 grid that has directions where the sidewalk's going or else zeros, because otherwise you just write a 0 into it. And your interpretation is 0 means go straight ahead, but arithmetically 0 means don't do anything. So that's where I'm going to start on this problem and see what happens. And maybe it works and maybe it's terrible. But if anyone has any thoughts on that, that sounds like a terrible idea, Colin, let me know, because I'm not sure. But I know my problem is that I need to make it be something that's real-time trainable, and it's got to be something where I can take video and make it into something that seems more meaningful. And there's always biological imperative from your retina and so forth that pre-computation is a real thing and it really works for people. And not everybody's got that enormous amount of video data like Google would. And you can do that problem, but you probably only need like 16 million hours of driving a car in order to accomplish it. So I don't know. I think it's an interesting challenge to have a real-time trainable, drivable robot. So if some lady gets run over with this robot, then you'll know why, because 8x8's not enough. Like, he did not drive himself very well.
That rock looked like a sidewalk, so.
No ladies with white blouses yet to be in the frame, because they'll drive straight into them. So I don't know, that's the status here. I know this presentation's like all over the place because it's like cache and subsampling video and whatever, but we can look at some performance. One is on Raspberry Pi and one's on an i5, and you can see very quickly that if you wanted to do math, you're not going to pick the Raspberry Pi. The i5 dramatically outperforms it, which is curious because you think the Raspberry Pi is at 1 gigahertz and the the i5 is 3. So you'd think it would be about like a factor of 3 different, but it's way more than a factor of 3 different between the two.
Plastic bag was a good idea.
It started out just being for keeping it all together, but it does seem to have turned into a very good plan for the weather. This is kind of funny how you used to bring the Chromebook, and it's now been,
You know the HDMI cable?
it looks like it got over here somehow. It's been completely replaced by just bringing the Raspberry Pi. That's strange. Is this a weight-bearing
Yeah.
surface? There it is.
See if I can help you out here.
Maybe I should reboot the whole guy. Cancel my dollar.
There you go.
Can you see it for a second?
Yeah.
And then I kill it.
Well, it's not going to raise the network interface. It's not very good about stopping halfway through.
Mr. Cole, I think one of you.
I think it tries for like a minute or some absurd amount of time.
A minute and a half, I think.
A minute and a half, that's too long. Should have done this before it started.
You're shot back to the store.
I think they bring a shot back. It's bottled water.
And ours are theirs. He's gonna bring his over.
He's.
That'll stop here in a second. I don't know why I feel so excited about making attempts to. This is probably a personal user error, not setting Raspberry Pi up right how well is going on all the time. Alrighty. So, there's an i5 in the middle column. It's a fourth generation i5. He's got a 6 meg 12-way L3 cache, 4 cores, and 4 independent 256K 8-way L2 caches, and a per core 32K 8-way L1 cache, one for instruction and one for data. Raspberry Pi is, and the cache line is 64 bytes. Raspberry Pi is 1 gigahertz, has a 256K shared 8-way L2 cache and a 16K 4-way shared L1 cache. So if you're not optimizing anything and you're doing this cache line test, this is all single precision arithmetic. So this is going every adjacent single precision, every 4 bytes. And this one skips 1, this one skips 3, this one skips 7. And so since it's single precision 32-bit floats, the i5's cache line is at 16 floats. And so after 16-ish, like really kind of dramatically drop off from having a reasonably fast sort of floating point operation to fairly slow ones. So you can kind of see it. I mean, most of these things are we telling the compiler to align thing on the stuff on the cache line? I didn't for the non-optimized. For the optimized I do, but for this I don't. So it's not quite as clear where it drops off. And on this fellow, it's kind of funny. Things aren't aligned on the cache line. The cache line's actually at 4. So you don't even notice anything until you get to this larger value. So I don't have a good explanation for why it drops off suddenly here. But there's a pretty noticeable difference. Say you're using the one that goes with 1. There's a 3-time difference in the CPU clock speed, but there's a over 10 times difference in the floating point computational speed. And it gets much, much more severe whenever you start optimizing. So for this guy, he will drop off the cache line after 16. So he gets kind of slow, but on these, he's really doing an excellent job because the core is relatively fast compared with the speed of the memory. So you can take a lot of advantage of things that are doing a lot of arithmetic operations within that cache line. The Raspberry Pi just sort of isn't as good for numeric crunching at all. It's pretty bad. Even optimized, it has about 20 times worse performance. For the cache size, first it looks at a sequence of 256 floats, and then 512, then 1024, and so forth. So this guy has a 64K L1 cache, which is at this 16K point, because this is the number of floats. So right here, the i5 drops from being able to compute things in L1 cache to not. So if it's in L1 cache, you're getting something over about a gigaflop performance. And once it hits L2 cache, you're getting more like half that performance. It has a 256K L2 cache, so after it gets to 65,536, it drops out of L2 cache and L3 cache. So you're actually getting a pretty good performance, only a third as much as the best when it's in L1. But when you get to main memory, it's less than 10 times as fast. This really makes me feel like a weatherman doing this. Over here, on this side of the country, with the Raspberry Pi,
There's flooding.
there's flooding, and it's very consistent. And the thing that's kind of funny is since it's got this 16K cache, you can really see it between these two lines. One's 80 and one's less than 40. So that's where it fell out of L1 into L2, and then it fell out of L2 to main memory, right where it starts getting this very consistent 13. So you get a whopping 13 megaflops out of main memory on a Raspberry Pi. But it's not that much more awesome if you have it out of main memory on the i5. What you need, if you want big problems, is you need faster RAM. This box has PC1333, so if this box wanted to do bigger problems and have any kind of better performance, it's not doing anything better with the processor. It's not investing in a better processor, it's investing in faster RAM. And the fastest RAM is only about 2.5 times faster than PC1333. So, I mean, you really just have to do that. If you're doing small problems, then you should kind of focus in this Midwest area here where it's raining. But, can't help it. I'm sorry, I'm very silly. On this pipelining example, there's one operation repeated 4 times, 2 operations repeated twice, and 4 operations that are not repeated. And when it's not optimizing, ooh, don't look here because this is awesome performance. When it's not optimizing on the i3, they all do pretty well because the pipelining on the i5 works pretty well. And it works pretty well on the Raspberry Pi too. The funny thing is how good of performance you get whenever you have optimizations that'll take advantage of the vectorizing instructions. This one is cheating. It's not actually that fast, but the compiler noticed that you're doing the same incrementing operation twice, so it just replaced it with +2. So this one's kind of compiler helping you out and taking advantage of that it can notice patterns like that you really have no problem with making that replacement, so it can help. But I left it in there like that because that's great. It's misleading that it actually does something faster than it does, but it's really cool that the compiler can determine simple substitutions to make your code faster. And this is what I would like to see on code that I would be writing. I would love it if everything ran at 3 gigaflops. And funny thing is, the Raspberry Pi has a little bit more erratic behavior on that. And I don't have a good explanation for why repeated instruction on Raspberry Pi works more poorly than 4 separate instructions in 4 different memory locations, other than the Raspberry Pi has relatively fast system memory compared with i5. i5 processor is way faster than Raspberry Pi compared with memory, so that trend might have to do with that. This one's doing an operation like WXYZ, and then doing it interchanged a little bit, and then only doing the 2. And funny thing is, when you're doing it on an i5 and you only do the 2 instructions, it really doesn't do a very good job accommodating that you're doing half as many things, and the loop that it's in It doesn't give you any real speed up, but strangely enough, the Raspberry Pi did a better job on that one. But when you turn on the optimizations, the i5 just flies. And, I mean, relatively speaking, the Raspberry Pi had a huge improvement by about 10 times, whereas the i5 only went up by 3 times. But it did better, strangely, when it vectorizes those instructions on an i5, because now it runs at 2/3 the speed, and there it was running at half the speed. I mean, that's one of the things you've kind of got to trial and like reason about it, and trial and error it in order to eke out the best performance. Threading is kind of a funny story, since the memory on the Raspberry Pi is relatively fast. It doesn't make a huge performance difference between hitting in the cache line and not in the cache line, but on an i5, since the main memory is relatively slow, whenever you're hitting the same cache line, you have somewhat worse performance than hitting a different cache line on a threaded application. We can look at this here in a second, but for the OCaml native is using OCaml's built-in structures for basically pairwise, element-wise adding 2 arrays. And if you do it on the Raspberry Pi, it clocks in a whopping 5 megaflops, so it's like 30 times faster on the i5. If you write a just real sort of straightforward, doing it in C for exactly the same operation using the same OCaml types, you get about a 2-time improvement in speed. And then if you turn on, if you do it like really crank it up and use like the best way of packaging your single floats and stuff like that, then you end up with a pretty substantial increase in speed. So I think this is a good demo of why you should bother making tuned add-ons to your favorite language, because you have something that's doable. I mean, you can compute a lot of stuff with 142 megaflops, but you can do a lot better if you have almost 3 gigaflop performance. And the I just make an array, and then I use the map function to, I don't even store the result, but just do the pairwise adding on the things. And then whenever you're doing something, we'll just skip to the way you declare it is you just say, I'm going to have an external function, give it a signature that's what you're using, and give it a name to use, or the name that's the external name. And then you can just call it and use it like any other OCaml function. And you include the OCaml library stuff. It has some macros that help you with passing values. You can declare how many values you're using internally, which are basically the ones that you pass to it. And what that all does is it lets you break up some of the types from OCaml, and it invokes, you know, it takes care of the garbage collection stuff. And then in this case, I just was passing in a pointer to a bunch of single floats. And then you do your nice tight loop, and your optimizing compiler will make it very nice and fast for you. And then this one is fast in part also because it doesn't package up a return value, it does it in place. But you want to have a type that's basically a pointer to a contiguous block of memory with just numbers in it, and then be able to do as much in place as possible. But if you do it, it's worthwhile because it's like 20 times faster. And that was for a problem that had 1 million floats, so it's not like it's even attempting to fit into L1 cache or anything. It barely fits into the L3 cache on that machine. So that's all I've got. And I will post code and stuff. Performance tuning is a fun game. It's a little frustrating sometimes, but it's a fun game. Are there any questions, concerns, comments? or does anybody need one or two or five more tamales?
Always.
There are take-home tamales for home.
Take home donuts too.
I need a nap. That's what I need.
Molly.
Where can I find your postings?
I
I
post.
haven't really looked into the group
Mm.
much yet, so.
I, like on the particular meetup page, like for this meetup, I'll post in the, I don't know, maybe it's called comments or something. I'll post in the comments about
Okay.
what the,
Should I stop it?
yes, please. I will post a link to GitHub and a link to, whatever else seems good about it at the time, but definitely to GitHub. And it's basically like this, this stuff. It's got these example OCaml things, which there's been a history of doing things in OCaml for the last few times, so it's not a very good starting point necessarily.